This is A2Further. Notes we're in chapter 6. We're looking at differential equations, specifically here second order differential equations, and this is our second video on it. On the first video we were looking whenever this second order differential equation equals 0, and there were three possible options depending on the three possible options of the auxiliary quadratic equation, whether we had two real roots, one repeated real root, or complex roots, meant then for different forms of our solution. Here we're looking then whenever there's a function of x at the end. So we always deal with the first bit first and find our AQE and find our solution, and then we look to find in the specific bit whenever it's f of x. So f of x can take three parts. It can either be just a regular, what would you call it, a polynomial, and then maybe an exponential function or a trig function. And we have that then. So to solve an equation of the form like that, first of all, solve the equation obtained by replacing the right hand side with 0, and then add to that solution some extra term to produce the terms of f of x. These extra terms are found by following some general rules depending on the form of f of x. The general solution will consist of two parts. The solution, whenever you put it equal to 0, that was their previous video, we'll look back at it if you need to. This part of the general solution is called the complementary function. The extra terms required, then the second bit is the extra terms required to produce the f of x. This part is called the particular integral. We can now consider particular integral for three different ways: a polynomial, an exponential, or a trig function. Note, if the question gives some initial conditions, then these are used to find the constants a and b only after the complete general solution is found. So we go all our way through, find our complementary function and our particular integral, and then we use our boundary conditions then to work out what we have. Part A then, if f of x is a polynomial. So consider this one here equals 9x plus 6. Again, what we do is we let it equal to 0 first of all, and we find in the complementary function bit. So we put that equal to 0, there's our AQE, and we get 1 and 3. That means our complementary function is the form y equals ae to the 3x plus be to the x. Extra terms required will be of the form px plus q. So I've looked at the 9x plus 6, and I think then I'm going to try y equals px plus q and try and work out then from there. So if I have y equals px plus q and I differentiate that, I get dy by dx just equals p, and I then get, make sure we can see both of these if I can set it up properly, yeah, and d2y by dx squared equals 0. If I substitute that into the original equation, which is up here, remember d2y by dx squared was 0, and then this was p, and then this was px plus q, so that's what I'm substituting in here. 0 minus 4p plus 3 upon px plus q, and we can suss out then from there. If you equate the coefficients of x, you can find that p is 3, and if you equate the constants, you find then that q is 18. So the particular integral that we're looking for is 3x plus 6, which is the extra terms at the end. Then the general solution of equation 1 is y equals ae to the 3x plus be to the x plus 3x plus 6. In general, if f of x is a polynomial of degree n, then the particular integral should be a polynomial of degree n. So that's our part A. That's if the extra bit, then the particular integral then is a polynomial. Second part then, if it's exponential, so you'll note we have the same complementary function, but we're going to get it out because the same numbers here, but then we have 10e to the minus 2x. So let's see then where this takes us. d2y by dx squared, as ever, we work out our left hand side first, and we get it, it's just the same one as before, y equals a to the 3x plus be to the x. Here it's 10e to the minus 2x, so looking at that, I'm going to try p equals e to the minus 2x. I'm going to let my y equal p to the minus 2x again, I'm getting that from up here. Differentiate this, I get dy by dx is minus 2 pe to the minus 2x, and d2y by dx squared, then differentiating this, I get 4 pe to the minus 2x. I'm going to substitute these three things into here, and we end up with what we have here. 4 pe to the 2x plus 8 pe to the minus 2x plus 3 p to the minus 2 is 10 e to the minus 2x. Simplifying the left hand side gives us 15 pe to the minus 2x, 10 e to the minus 2x. 15p is 10, and p then is 2/3. That means the particular integral is going to be y equals 2/3 e to the minus 2x. And our general solution then of the whole thing is y equals a e to the 3x plus b e to the x plus 2/3 e to the minus 2x. That's for part A. Then was a polynomial, part B was an exponential function, and finally in part C if it's a trig function. So let's take a look at them and how it works for there. Again, we have the same first part, so it's going to give us again the complementary function, which is y equals a e to the 3x plus b e to the x. By observing the right hand side, I'm going to try p sine 2x plus q cos 2x, again from looking at this, so I set my y equal to that. Differentiating this gives us 2p cos 2x minus 2q sine 2x, and then differentiating this gives us minus 4p sine 2x minus 4q cos x. Substituting all this into this starts to get a little bit messy, but we have this, so d2y by dx squared is this bit here, that's there. Take away 4 upon dy by dx plus 3 upon the y equals 10 sine 2x plus that. If we get things with sine 2x in them, we have minus 4p plus 8q plus 3p is this sine 2x bit here, and then for the cos 2x part, minus 4p minus 8q plus 3p gives us their 15, and we end up with then two equations, two unknowns that we can solve, which gives us, I'm not going to do it now, but with p equals minus 2 and q equals 1. So the particular integral is y equals minus 2 sine 2x plus cos 2x, obviously getting from our minus 2 here and our 1 here, and our general solution then is y equals a e to the 3x plus b e to the x minus 2 sine 2x plus cos 2x. In general, if f of x is of the form a sine kx plus b cos kx, then the particular integral will be a similar combination of these terms. There's really 6 things you need to remember. The first 3 are to do with the AQE and the solutions that come out of that. Obviously 2 real solutions has one format, a repeated root has another format, and complex roots has another format. And then within that there are 3 possible right hand sides. So this was the trig one here, the part B was the exponential, and the part A was that. So you have 9 really possible options. You can have any of the first 3 and any of the last 3, which give you 9 possible options with 6 things effectively then to learn off. We're going to go through another couple of examples in the next 2 videos, so you can take a look then at those.